start recording. Okay, so we're gonna go over a final review of is soundboard on. I don't think you can disable it for Discord, but I just disable the sound, so I cannot hear anything. If someone else is abusing it, please tell me. Yeah, you can mute it personally. I think it's a little stupid. You can't mute it totally, but whatever. We're gonna be going over 2020. Yeah, the final exam for 2020 for ELE302. Now it's a little odd. I don't know if we're also going to be doing it, but there are two questions on here that are midterm questions, right? There's one question that is second order RLC and one question that is Bode plots. Yeah, so I already did those in the midterm. I won't be going over them again. So we're going to be going over question 2, question 3, and question 5, and question 6. So that's going to be in order. We're going to be doing Laplace transformation for second order RLC, magnetically coupled circuits, three-phase circuit, and Fourier series. Chances for Bode on the final. I don't think we'll see Bode on the final. I think Kilger probably knows more than me on that, but I'm doubtful because we already did on the midterm. Right? If we hadn't done it on the midterm, probably would be on the final. They also did say no filters, right? Yeah, no filters. So let's start with the first question here. Let's make it a little bit smaller. Laplace transform. Use Laplace transforms for finding I in terms of t greater than 0. Write a second order differential equation in terms of IT to show the above circuit. So you still need to know a little bit of RLC. Like it says here, they want you to do second order differential equation. Is this on the D2L? No, unfortunately they did not distribute this. Here, I'll distribute it out because I got sent it by a lot of people actually. So it's just been sort of circulating around. There you go. 2020. Now, oh, by the way, there's no solutions for this. So I've double checked all my work. I haven't double checked all my work, but I've, checked to make sure that I'm on the right track. If it seems like I'm doing something wrong, or if you did it yourself and you're not getting the right answer, please point it out. So for question 2A, this is double check. Yeah. You don't know how many silly mistakes I make. Okay. For question A, write a second order differential equation in terms of IT to describe the above circuit. So you have to so let's draw the circuit at time greater than t. Nothing really changes because the only thing that changes between them is the voltage amount. Before at time 0 it's 10 volts and after time 0 it's 20 volts. So this is t greater than 0, right? It passes through the resistor, passes through the inductor, and then passes through the capacitor. And then all the way back around. Very simple circuit. Nothing crazy. Let's move that down a bit. And so it's asking for the current through this. So remember, for second order circuits, if it's asking for the current, you use Kirchhoff's voltage law. So that's mesh. If you're trying to find voltage, then use Kirchhoff's current law, or nodal. Let me just highlight that in red for you. So we are trying to find IT. So we are going to use mesh analysis. It's also the easiest one, as you can see. So let me just write out here. This is going to be 6 ohms, 1 Henry, and 1/25 of a farad. So this one should be rather straightforward. We're going to start at the voltage source. We're going to assume this current direction, as always. It's going to be 20 minus the current times the resistance, minus the voltage passing through the inductor, minus the voltage passing through the capacitor is all equals 0. We're all clear on that, right? This is midterm content stuff. And then now you start using your second order RLC equations. Remember, you take for inductors, and then for capacitors, you're going to have IC. Is Bala or Andy writing the final? I believe for this year it's going to be Bala. But double check that. So these are standard equations. You know how it is. And we are trying to isolate for current. So we could turn the voltage here into current, but we need to flip this equation. So we are going to do the integral of IC dt 1 over L is going to be equal to VC. All right, now we can substitute these in here. And we're going to get 20 minus IR minus VL, which is Li prime, minus 1 over, sorry, my bad. I wrote L here. This is supposed to be C. 1 over C integral of I dt is equal 0. This arrow's getting in the way. Sorry. And now we derive the whole equation. So when we derive it, this 20 goes to 0. We're left with I prime R, or actually let's leave the constants out front. So it's R I prime minus L I double prime minus 1 over C I is equal 0. And now we put it in standard form, so I double prime should have a coefficient of 1. Is this Laplace? No, we're still doing normal second order circuit. So the question here, it says write a second order differential equation. So it wants you to do the same thing that you've done before on the midterm. And then we do Laplace. I think the way that they sort of make us do it is a little dumb, but you know, that's what the question asks, unfortunately. I'll show you the faster way at the end, but on the test, they will ask you for each one of these steps, so you can't take shortcuts. So we isolate, so I double prime has a coefficient of 1. So let's put I double prime at the front here, plus R over L I prime minus 1 over CL I is equal 0. Why can't we just convert the entire circuit to Laplace? Yeah, exactly. That's what I'm saying, is that they make us do all of this when you can just convert the circuit to Laplace. I'm not exactly sure why. If it doesn't ask you for a specific method, then you can do that. But in this case, and in all of the finals I have seen, they ask you to write the second order differential equation, which means you have to do second order stuff first. I'll show you, isn't it negative R over L? Oh, sorry. I multiplied this entire equation by negative. So I multiplied this entire equation by negative 1 over L. This part is just multiplied by d over dt. And this part is multiplied by 1 over L. Negative 1 over L. Because your goal is to have this coefficient be 1, just 1. And you can see here it's negative L, so to cancel that, negative 1 over L. Okay, that's it. We have determined a second order differential equation for the question. So that's A done. Now part B, derive an equation for I of S using Laplace transforms. Now we do Laplace. Attendance numbers are kind of low. Yeah. Oh, you mean in this tutorial? I don't usually look at the number of people, so I never noticed. But I think it's just that there's There's study hall for 318 going on right now. I don't know, maybe half of the course dropped. Or maybe no, I did ping. 318's in an hour, yeah. I did ping for it, so it's probably just the other thing. Don't you have to put the numbers back in the equation? I'm not too sure what you mean by that. I pinged it in announcements. You should have received it. Just check announcements. Um, I'm not sure what you mean by putting the numbers back in the equation. Oh, you mean like filling it out? You can do that. Probably on the final, you should probably be doing that. That's a good point. But I like to just work with the I like to work with the variables because then it creates like a generic thing that you can just fill in everything at the end. But we could do that right now. You're gonna get 6 I prime plus 1 over LC or CL, which is just 25 I is equal 0. So that's our second order equation done. Now we're going to derive an equation for IFs using Laplace transforms. So this is just Laplace. You should know how to do Laplace. So on this end, you're going to get s squared capital I of s minus s of lowercase I. So that's the unLaplace one of 0 minus I prime of 0. So that's this part. Actually, you know what? Just to make it a little bit more clear, I'm going to highlight each part one by one. Let's copy this down here. So this red part, orange part, and let's call this blue. There you go. This orange part is going to be 6 times I of I of S, minus I of 0. And then you have the blue part, the 25I part, which just becomes 25 of IS. Let me double check just to make sure I'm not waffling because I'm very prone to messing up. Yeah. So do we get a Laplace table for the final? Yes, you do. If I look on this one here, you get useful Laplaces on the back. You should know it. I'm sorry, but it is there alongside the Fourier series equations if you need them. So this is our equation here, our Laplace equation here, equals 0. Okay, and now we just need to simplify and bring out the I. So you know how this is. You isolate for I of S. You're going to receive on one side I of S times S squared plus 6S. Is that, yeah, 6S plus 25 minus I of 0 times S plus 6 minus I prime of 0 is equal to 0. And once again, you just isolate for IS. You're going to receive that IS is going to be equal to S plus 6 on top, I of 0 plus I prime of 0 over S minus 6? No, it's S plus 6. Yeah, it's plus 6. Negative S? I'm not sure what you mean by that. Negative S, yes. Negative S, yes. However, we're moving it to the other side here, right? Remember, everything here is on the left side. Now we're moving it to the right side, so we flip the sign. If you want to, I can, let me just put in a intermediate step here. Question, yeah, what's up? What do you do for I of 0 and I prime of 0? We'll do that in the next part. Right now, it's just there. There are initial conditions. We figure them out after. Yeah, even though we have Laplace, we still need to figure out the initial conditions. You always have to. But right now, we're just deriving an equation. We're not solving for the initial conditions. So on the bottom here, again, we just moved it over. It's going to be 6s plus 25. Everyone understand how we isolate for I of s? I'll take that as a yes. Okay. And that is our equation using I of s for Laplace transforms. This is just Laplace. I don't think there's anything special about it. If you could do the math midterm, you should be able to do this. Now we get to the next question here. But again, if you don't know a part, if it's not clear, say something. Yeah, that's a fair statement, but like... The only complicated part is this part where you Laplace it. The rest is algebra. And which these are on your table, right? If you look on your table here, the double derivative of I is going to be that, all that stuff. It's all here. It's just following it. Is the tutorial recorded? Yes, it is. Unless, you know, I lose the audio, but it is being recorded right now. I will upload it later. So yeah, you Laplace it, and the rest is just algebra here. Anyway, C. Find I greater than t seconds by determining inverse Laplace of is determined in section B. Okay, so now we need to find the initial conditions because you can't determine the inverse Laplace so long as we have these initial condition values up in here. So to do this, we're going to need to find the, well, initial conditions. Let's redraw the circuit at time less than 0. You always start with time less than 0. So we have a resistor, we have an inductor, which just becomes a short circuit, and we have a capacitor, which becomes an open circuit. And it's asking, okay, so we have the resistor here. Now we have no current. And remember, when we have no current, the resistor is pointless, right? Because the voltage drop across the resistor is current times resistance. We have no current, we have no resistance. Or sorry, we have no voltage drop over the resistor, so it might as well not exist. And this has a 10-volt source. So now we need to determine the current passing through the inductor and the voltage passing through the capacitor. These ones are pretty simple. There's no current, so the current is 0. So IL at 0 minus is going to be 0, and 0 amps. And the voltage current at 0 minus is going to be 10 volts. Everyone knows how that works? Again, this is just second order equations. And so now we have one of our initial conditions. Now it's time for a second initial condition. This one, we're going to be doing time is equal to 0. Sorry, let me just move this all up one. There you go. Sorry. I guess I'll just redraw it. Plus and minus. We have our resistor. Our inductor, because we're at time 0, so we can't assume steady state anymore. We can only assume steady state well before 0 and at infinity. This is 20 volts. We have our resistance R, which is going to be... What is our resistance again? It is 6 ohms. 6 ohms, 1 Henry, 1 over 25th of a farad. And so, remember how it works. So the current is maintained, and so is the voltage at this point. So the voltage across this is going to be 10 volts. But the current across this is going to be 0. Oh, it's going to be 0 amps. So if in that case, we need to find the voltage of the inductor, which we can turn into the current. Right? Let me write that in red. So voltage of inductor, we turn that into the current across the inductor. The current prime over the inductor, actually. Yes. So we need to find the voltage over here. If the voltage over here is resisting by 10, and voltage over here is adding by 20, but, let's do the long way. Let's do a KVL. That's going to be 20. Current's running this way. Minus IR. Minus the voltage over the inductor. Minus the voltage over the capacitor. This is 10. This is going to be 0 because we have no current. Oh, and this is all equal 0. Therefore, the voltage of the inductor is 10 volts. And so, now we just put that into the equation. So VL is going to be 10 volts. And we know that L, di over dt, is equal to VL. Therefore, you have 10 volts over the inductance. You have 10 over the inductance. The inductance is 1, so we just have 10. Therefore, I prime is equal to 10 amps per second. So now we have both of our initial conditions. And, okay. So let's take our equation that we formed here. We're going to put it up here. And now we fill it in. So here, let me bring that down one more. We have I of 0 here is 0. And I prime of 0 here is 10 amps per second. So we fill it in. This is going to be 0. And this is going to be 10. We're going to get I of S is equal to 10 over S squared plus 6S plus 25. Now, can you factor this? You cannot without complex numbers. And frankly, I don't like complex numbers. Complex numbers are scary. So we need to complete the square. And I know some people have trouble with this, so I'm going to run through how you do it. First of all, what you do is you just take this section. You ignore the third part. You have S squared plus 6S. This complete square. Cannot factor. Right? So we have S squared plus 6S. Now we put that into like so. S plus 3 squared. This is just 1/2 of this amount, so that's going to be 6 divided by 2, 3. Let me put that in red just to show. There you go. 1/2. Now what you do is you expand this out again. When you expand out, you're going to get s squared plus 6s, that's correct, plus 9. At this point, now you take the 25 and you need to add some number here so that this amount is equal to 25. Well, what's that number? 16. And once again, you take this number outside and you fill it in. This seems a little, yes, it's just yes. There are formulas, but I like to do it this way because it shows you the sort of thought process behind it. So I hope everyone here can understand, because I know some people struggle with completing squares. You divide by 2, you expand it out, you fill it in so that it adds up to your original equation, and then you put it all back together. So your IS here at the end. Why do you complete the square though? Because we cannot anti-Laplace this. We don't have the ability to anti-Laplace a quadratic. We have to what do you call? We have to either split it up through partial fractions or by completing the square. We can't do partial fractions here because it is not it has no real roots. So we can't factor it. So we're going to end up with 10 on top. S plus 3 squared plus 16. Now, again, this is just anti-Laplace. Whenever you see all of your stuff like s plus 3, s plus whatever, that means that there's a shift. So to anti-Laplace it, we're going to end up with I of t is going to be, let's take out the shift, so it's going to be negative 3t times the Laplace of the rest of it. Or is it we anti-Laplace? Let me just fill that out. There you go. So the anti-Laplace of I of s is going to be I of t, lowercase I of t. We unshift this out. I just highlight that. There you go. And we have the rest, which is going to be 10 over s squared plus 16. Ooh, let me just fix that. There you go. This is in your Laplace table. This is just Laplace for sine. And when you fill it out, you're going to get 5 over 2 e to the negative 3t sine of 4t. Do you think this is the easiest question on file? No. I would say 3-phase or the Fourier is probably the easiest. Because those ones, they're just math. You just follow formulas. They're real simple. This one, I'd say, is second hardest. I'd say, if you don't do this, at least get 75? Probably. Probably. That's assuming you do it right, obviously. So, now, yeah, this is just anti-Laplacing. And you get your final answer here. And that's the answer for C. So everyone follows this sort of thought process on how to do this. What's a Laplace? You're cooked. Yeah, go back. Okay, and now, question D. And this is what really annoys me. Now it asks you to draw the circuit in Laplace transform format. Where is it? Using Laplace transforms, draw the Laplace circuit. Draw a transformed circuit. So you need to know how to do this, but they don't make you do this method, and this very much annoys me. Anyway, so here are the rules for a Laplace transform circuit. Are we going to get these kind of questions on the exam exactly? Yes, they will be very similar. I don't think so. I don't think Bala is the kind of person to switch up his exams every year. So you should really expect this kind of stuff. Okay, so is it because this question doesn't have much to change? Yeah, probably. The most that will change is whether or not they'll ask for the current or ask for a voltage. If they ask for a voltage, it's going to be a different circuit, kind of like what you saw in the midterm. But if like you can see my previous I believe my previous tutorial for the midterm, I did a second order RLC that's voltage. What if you get fucked up circuit? You try your best, man. I don't think you will. But what I'm telling you here is applicable to all of it, right? If they give you a fucked up circuit, what it means is you'll have to do two mesh equations, maybe. It's the same process. It's same equations, it's same Laplace, it's same anti-Laplace. It's just different starting point. The only parts you truly need to remember for this are the second order, converting it to second order RLC. So these equations up here, the methods you use. You need to know how to Laplace. You should know how to do those. What if we get a super mesh? I forgot how to do those. Then you should probably study how to do super mesh. It's one of my previous tutorials. You can search it. You should know how to get initial conditions. And you should know how to anti-Laplace. That's all. Okay, now using Laplace transforms, draw a transformed circuit. Let me see if it tells you. It does not, sadly. So, finding Vs from Is is 1 over... I wouldn't know. If I show that there. Yeah, I wouldn't know too well. I just use KCL if it asks you to find voltage. If it asks you to find voltage, you do KCL. If it asks you to do find current, use KVL, mesh analysis. Anyway, question D. Okay. So using Laplace transforms, draw a transformed circuit. So the rules for this, if you have a voltage source, so we have the time domain, and then we have the S domain, right? If you have a voltage source, this with some voltage V, in the S domain, it's going to be V over S. All right? If you have an inductor, let's say the current is traveling downwards at time 0, so this is going to be the current through the inductor at time 0. Then on the S domain, you'll have your inductor here, and then you'll have your initial condition for it. And this voltage source will go the same direction as the current. So this inductor here, this inductor is L. This inductor is going to be LS. And the voltage source is going to be VL at time 0 divided by S. Sorry, no, IL. Oopsie. IL at time 0 divided by S. If you have a capacitor, and let's define this as positive side, this is negative side. Actually, no. Yeah, this is positive side, this is negative side. C. And this, you're going to have VC at 0. In time domain, you're going to have the capacitor and a voltage source. And these ones will align the same as your prong directions. This is going to be 1 over CS. And this is going to be VC of 0 over S. Before anyone asks, you kind of just have to memorize this. I'm sorry, but you kind of just have to memorize this. And then you have the resistor. And in S domain, it's going to be the exact same thing. No change. Write it on the back of your calculator. Yeah, that's called academic misconduct. For legal reasons, I don't support that, and you really shouldn't be doing that. Hypothetically, yeah, sure. Anyway, is S domain the Laplace version? Yes. So the Laplace of the time domain is going to be the S domain. So, let me get the original circuit up in here. And now we just convert it to S domain, right? So we have our voltage source here. And what did I do for this? Yeah, so this is all for time greater than 0. So when you do the Laplace thing, it's for time greater than 0. So this is going to be 20 volts divided by S, right? It used to be 20 volts, now it's 20 divided by S in S domain. You take this up. Actually, let me move this a bit down. There you go. We have the resistor. Nothing changes about the resistor, so we have 6 ohms here, or just 6. You pass through the inductor that has a single Henry, so it's going to have S. You pass through a voltage source, and the current is flowing this way, so that's the alignment of the voltage source. Now, the current at this time is 0. So this just disappears, right? Because that gives 0 voltage addition. And then we go through the capacitor. Someone have their mic unmuted? Oh, yeah. Yeah, no worries. It's just, could hear it. Anyway, we have the capacitor here. It's going to be 25 over S, because it used to be 1 over 25. 1 over 1 over 25 is 25 over S. Then we go through another voltage source. Where's question rank in terms of complexity? I would say second most hardest to hardest. Depends on how well you find magnetically coupled circuits. So, yeah. Anyway. And once again, this is going to be VC at time 0 over S. And VC at time 0 is 10. And now you've made your circuit, right? Let me just copy over for a cleaner circuit. So we get rid of that. This is going to be 10. There's your circuit. There's your Laplace circuit. And so we can verify this. We can verify this because we can just do mesh analysis on this, right? So let us do mesh analysis. Just for checking. We don't actually have to do this. Right? So we pass through 20 over S. We subtract 6 ohms times I, capital I, because we're working S domain, remember? Minus SI, minus 25 over S, minus 10 over S is equal to 0. And if you factor this out, if you isolate for I, you're going to eventually end up with I is equal to 10 over s squared plus 6s plus 25. Would you look at that? This is how easy it was. We didn't have to do all of this stuff, but they make us do this stuff. Well, you still have to still need to find the initial conditions. Actually, no, you don't. It's given. Oh, wait, no, you do. You do for these. Anyway. So, this is the faster way of solving it, but they want you to do the slower way. You can jump straight to part D, yes, but the questions will specifically ask you to do it in that way. And if you don't, you're going to lose marks. So you have to do this way of doing the second order differential equation and then deriving the expression and then all of that stuff. Okay. Is that 2s over s or 25 over s? 25. I hope I could make that a little bit clearer, but let me move that. I try to distinguish my 5s and s's, but sometimes I fail. There you go. All right, 1 second. Let me just stop here for a second, just a quick second, just for the recording.